So looking at how to solve our first problem here, number 1, we'll go ahead and draw it on our breadboard area first. So I have positive, and that's going to connect down here to our breadboard. Negative. And we have R1, which is in series. And R2 and 3, which are in parallel. That will help us understand current flow. To solve the equation part of our problem, we're going to break it down. I'm not going to give you any numerical answers in this tutorial, but I'll give you variables as the answer. I can see R1 is 330, R2 is 50, and R3 is 50. So I can first start by combining this one into one resistor here. And I know the value of that resistor is going to be 1 over R2 plus 1 over R3. And that will be equal to, that resistor will be R23. To find RT, it's going to be equal to R1 plus R23. Then we can start solving the individual stuff for our equation. We can find IT, which is going to be equal to V over R. So my V is going to be my total voltage, so VT over RT. As we talked about in class, we see that R1 is in series with our circuit, so we know that the current through R1 is going to be IT. Now we can determine the voltage across R1, which voltage, of course, is going to be equal to I times R, and current is V over R. So my I, I'm going to use is I total, so voltage of R1 is equal to IT times R1. Now that we know the voltage drop of resistor 1, we can determine the voltage drop of resistor 2 and 3 together because they're in parallel. And we know that voltage across resistors in parallel are the same. So voltage of 2, 3 is going to be equal to our total current again, IT times R 2, 3 from up here, 2, 3. So I have V, which is V 2, 3, and V 2, 3. After knowing those two voltages, I can determine the amount of current each one of those voltages are going to cause to run through resistors 2 and resistors 3. The formula for current, again, is going to be V over R. So the V I'm going to use for this is going to be V 2, 3 over R2 and V 2, 3 over R3. So now we're going to try solving problem number 3, the multiple series resistors in a parallel circuit. and I'll draw the breadboard first. Just like I did before, I have my negative breadboard, side of the breadboard with the jumper, and positive. For this one, since they're all in series, connected to the battery voltage over here, they're pretty easy to draw. I can just go from positive on one side of my breadboard to the other. So I have R2 and R1. Then I have R3, 4, and 5. R3. R4. R5. Remember, you cannot run R4 on a single column on the breadboard because they're all connected. If you wanted to run it on one side of the board or the other instead of bridging the gap, you'd have to run it diagonal slightly and step over a column before you go down to 5. And then I have R6 and 7 the same way as R1 and 2. 6 and 7. As I solve this, I'm going to write in the values of those total resistances. Or as you solve this, you should redraw it and write in the values of the total resistances. Like on the previous problem, I'm not going to give exact numbers. However, I might use the size of the values found to help give you some logic statements to prove whether you're doing it right or wrong. So first we want to combine our resistor sets. And so we can add R6 plus R7, R3 plus R4 plus R5, and R2 plus R1. So that we know the joint of the joint amount of those resistor sets. And so that becomes one resistor of R6, 7, R3, 4, 5, and R1, 2. If I automatically look at my problem, I can see R1 and 2 are 208. These two will equal 280. 3, 4, and 5 will be 380. And then I see 6 and 7 will be 250. So logically I can see that the middle branch is larger by a significant amount than the two outer branches, which tells me that branch will automatically get the least current. These two other branches will have similar amounts of current, but shouldn't be the same because they're similar, but they're off by 30 ohms each. Alright. So now that I've got resistor 1, 2, resistor 3, 4, 5, and resistor 6, 7, I can solve for total RT. So we get 1 over R12 plus 1 over R3, 4, 5 plus 1 over R6, 7. Once I know that, I can then determine my current of my circuit. So I need IT, which is equal to VT, so 15 volts, over my RT. So once I know my total current, I can then determine the amount of current through each branch, just like you would any other parallel circuit. Because I know the voltage through each branch is 15 volts. So current through R1 and R2 are going to be the same. So we're going to call this A, just so I notated that they're match. The current through 3, 4, and 5 will match, so I'll call those B, just to remember the difference. And then 6 and 7 will match, and that will be C. That way I can automatically have red flags to see if I did something wrong. Alright, so current, again, is going to be V over R. And voltage, again, is I times R. And so my current through branch R1 and R2 is going to be V, which is our total. So VT over R for that resistance for that branch. So whatever R12 was. And this is going to be the same thing. VT over R12. However, you could always just write the other answer in because it's the same answer. Same with this branch. So we can do VT over R3, 4, 5. And that's the same thing here. And in R5 as well. And then R6 and 7. So we want the current, again, through, we're going to put an I here to make sure we remember what we're looking for. Current through R6 is going to be total voltage over the resistance of that branch, which is R6, 7. And then that's the same thing that goes in R7. Now that I have the current for each branch, I can solve each branch independently as it's its own series circuit with a 15-volt battery. So my voltage across my resistor is going to be I times R. And so to know the voltage drop of R1, I can use the current from R1 and then the resistance of R1. So voltage drop of R1 is going to be I of 1, 2 times R1. And then the same thing for resistor 2. We have I of 1, 2 times R2. And then R3, 4, and 5 are the same. We have I 3, 4, 5 from the previous problem times R3. And then I have I 3, 4, 5 times R4. And I 3, 4, 5 times R5. R6 and 7 is going to use the current from 6 and 7. And so it is I6, 7 times R6. I6, 7 times R7. And if you had the current values, you could just go in and plug all those in on your TI calculator and just keep reusing the equation and changing the R value pretty simply. So, for number 4, we're first going to draw it out. And I can see R2 is in series with the battery, and then the rest is in a series parallel configuration after that. So I'll go ahead and start my drawing. I have positive. I have negative. And I'll go ahead and use the jumper as I did before. throw some more colors on here to make it a little bit easier to see. So I have R2, and that goes from the negative side into my circuit. So I can do that same thing. I have R2, into my circuit. Then, from there, it branches, and R1 goes back to positive. That branch between R2 and R1 goes to R5. Which then branches off with 3 and 4 to positive. So, that's how one way you could wire it. There are plenty of ways you could wire this circuit differently, but that works. Now, as I said before, when solving this one, it's a good idea to redraw each step of the way. So I'm going to draw two different configurations that would allow you to solve it a little bit different, allow you to see it in a different light to make it easier to solve. So I have the one I showed on the board. And I'm going to move R2 so it's vertical instead of horizontal, just so it's a little bit easier to see its relationship. So we have R1, and R5, which is then in parallel series to R3 and 4. So we can see now it's a little bit easier to condense down. So first we need to find the total resistance. And I'm going to work off this drawing here instead as I do my calculations. So first I need to combine R3 and R4 to get them to one resistor that I can put in series with R5. So R3, 4 is going to be equal to 1 over R3 plus 1 over R4. Once I solve for that, I can redraw my problem. Put this in purple. Now, I know the value of R3, 4. I can just add that to R5 to get the value of that branch. So I end up with a new circuit. We have 2, 1, and 5, 3, 4. That there is equal to R5 plus R3, 4. Or if you wanted to write it out the other way, we could write it out as we did in class. as R5 plus 1 over R. We're just taking this down here, R3 plus 1 over R4. So once we are able to calculate those, we can then put this resistor in parallel with this resistor. And so it becomes, that equals 1 over R1, put all that in parentheses, plus 1 over R5, 3, 4. Now I could break out R5 through 4 back up into the formula here, but I'd prefer not to do that just for the purpose of not having to write it out. So this now equals R1, 5, 3, 4. And now to get RT, that is going to be equal to R2 plus R1, 3, 5, 4. So once I've determined RT, I can then find IT, which equals V total over RT. And knowing that, I see resistor 2 here is in series with the battery before it goes to parallel through 1 and 5 through 4. So I know that the current across resistor 2 here is going to be I total. And my voltage drop for resistor 2, again, voltage is I times R, and current is V over R. So my voltage drop for resistor 2 is going to be the total current times that resistance. So IT times R2. With that, I can use the rest of the information to determine the voltage drop of the rest of the circuit. So now I need to find information on R1. So when looking at the circuit like this, we see one series resistor and two in parallel. Well, let's combine these ones in parallel as we did down here, and it becomes easier because we have this being R2 and this being R1. So we know the amount of voltage in R1 is going to equal the voltage left of this branch because these two are in parallel. So the same voltage will be at both these sets of resistors. And current will divide up. Some current will go up R1 and some current will go 5, 3, 4. But first we can just look at this as one giant resistor of R1, 3, 4, 5 and determine what its voltage is based on its total current, being the same as the total current in the circuit. So current through resistor 1, we want the voltage through resistor. We'll be I times R, so IT times, and I can't use R1 here, I have to use R and use the adjoint of that since it's all in parallel. So that's going to be times R1, 3, 5, 4, which we had figured out from here previously. So I can use that same information down here. Once I have that information, I can then determine the current that R1 would pull off the rest of the branches, and I use V over R because this gives me my voltage drop of R1, V of R1, so I can then determine the current through R1 by saying V of 1 is going to be equal divided by the resistance of 1. So current through R1 is going to be V1 over R1, the actual value of R1, not the combined value. Now that I solved for R1, I can break it back out into this and find the current through R5. So right now I see current going all the way through R2, then splitting between R1 and R5. And so next we solve for things related to R5. Remember, I can start think about things logically. I can think of R1 gets the total voltage drop minus whatever was reduced by R2. That same voltage drop we'll also see through R5 and R3-4 added together from the original diagram. And so whatever my voltage drop across R1 was, will be the same voltage drop across this whole part of the circuit. So as I said before, I can see that R1 is in parallel to R5, 3, 4. And I'm going to go ahead and draw it. Now that I've removed R2 from the equation by determining what its voltage drop was as compared to the rest of my circuit, I can go ahead and take it out of the circuit entirely if I want to make it a little bit easier to look at. So I have my battery. And it's now in parallel with R1. And R, so we have 1 here and 5, 3, 4. By looking at it this way, I know my battery voltage here is going to be the same as the voltage across R1. So this becomes V of R1, because V of R1 is actually V of R1, 3, 4, 5. And so I can determine the current that goes through branch 1 by using that same voltage of 1, 3, 4, 5 over R1, and then the same current, the same thing for I of 5, 3, 4 going to be equal to V1 or 1, 3, 5, 4 over R, the resistance for that branch, because it's a parallel branch, so it looks much like this. So whatever R5, 3, 4 was, which was calculated previously in this step here. Because R5 here is in series with R3 and 4. Once I determine the amount of current in R3, 4, 5, it's the same current as R5. So current through R5 is going to be that voltage divided by R3 5, 3, 4. And now that I know that, I can determine some other things. I can also determine my voltage drop across R5 because I now have the current at R5. So just like I did previously, I can take that current and current of 5 times the resistance of 5. So now I've determined how much voltage R5 drops across my circuit, and I know the voltage drop of this and these two combined have to add back up to the R1 voltage drop. And then to determine the voltage drop of R3 and 4, I still use the same current of I5 because they're in parallel. So we go and since these two are in parallel, we don't use R3 or R4. We have to use the joint value of R3, 4. So current of 5 times R3, 4, and then the same value goes here. Because they match. Alright, and now that I know that I can use that value I just found to determine my current through those two resistors. So remember, this is V of R3 and V of R4. So to find current of R3, V over R again, so my V becomes my voltage of 3, 4, because it's the same thing. Voltage of 3, 4 over R3. And this becomes voltage of 3, 4 over R4. Now if you had all those values, you can actually go back in here and plug in a lot of these knowns back into all the equations to start finding all your unknowns. Thank you very much. I'll see you in class.